Hi and welcome to this new lesson. We've seen in the previous lesson how to create a neuron. The problem was that the neuron wasn't so precise. So it was supposed to tell us that our input was a vertical image, and instead it gave us a result much closer to a horizontal image. Our goal in this lesson is to train the neuron so that the next time it will be more precise. So we're going to understand what does really training a neuron mean, and we will see this visually. So I'm going to draw everything on the whiteboard as I did before, and we will see also later the implementation with the Python code. Let's start. Let's make a quick recap of the previous lesson. In the previous lesson we created a neuron which take the input, we created random weights, activation function and output. So let's see this slowly. First, we take the vertical image. We did some pre-processing, so we flatten the image, and the image flatten is just a single array, so we have just the image in one column, and the black pixel corresponds to 0 and the white pixel corresponds to 1. Then we generate a random weights. I just gave 0.5 per each one, but we could put any weights from 0 to 1, and they could be all different from each other. So the first one could be, for example, 0.1, the second 0.7, 0.3, 0.4, and so on. We multiplied the input with the weights, and then we made the sum of the value, and we got 1.5. Then we use an activation function. The purpose of the activation function is to tell us either if our image is a vertical line or a horizontal line. In this case, we use the sigmoid function, and it gave us a result of 0.8. 0.8 is much closer to be a horizontal line, so much closer to 1 than to 0. But we know that we gave a vertical line. So here we can say that our neuron is not correct, so our neuron is not so clever yet. So that's why it gave us a wrong result. We were detecting a vertical line, but as a result it told us this is a horizontal line. As we know it's not correct, the detection, now we have to understand how much are we wrong. To do this, we calculated the error. The error is calculated by taking the result given by the activation function minus the label. The label is 0 for vertical and 1 for horizontal. So we took the result 0.8 minus vertical, which is 0, and we got an error of 0.8. So now we have two values that we need to work with. One is the error, which is 0.8, and the other one is the result of the activation function, which is 0.8. It is just a coincidence that they are equal at the moment. They will not be always the same, and we will see that. Now we're going to use these two values to understand how to train the neuron so that it can be more clever, so that the next time the output can be better than it is now. So let's now work with these two values. We will take first the result of the activation function, which is 0.8, and also the error, which is 0.8 as well. Error is equals to 0.8. Now the question is, how, starting from these two values, can we improve the neuron so that it will be more precise? To understand this, we need again to take a close look at the neuron. On the neuron we have input, and the input is the image, so the input is always the same. Then we have activation function is the sigmoid, so this we cannot change the activation function to give a different result. It will give always the same result for the same value. The output, either vertical or horizontal, they will be always the same. The only thing that we can change is the weights. So this is the core of training a neuron. Training a neuron means adjusting the weights so that it will give the correct result. And now another question. How do we adjust the weights and how much can we adjust them? Because it's not easy to say just adjust the weights, but also how much do we have either increase this 0.5 to be higher, so like 0.6, 0.7 and so on, decrease it. And also do we have to change all of them or just some of them? That's what we're going to see right now. First of all, let's understand the concept of the neuron, how to train the neuron, looking at the sigmoid function. Okay. The idea is that after we take a look at the sigmoid, it will make sense why, first of all, we use the sigmoid and why we are going to adjust the weights in a certain way. So this is the sigmoid. The sigmoid goes from 0 to 1, where 0 is vertical and 1 is horizontal. We can also say that all the values that we get after we multiply the input with the weights that are less than 0, they will give a result on the sigmoid of less than 0.5, so they will be closer to vertical. All the positive results, so 0 to infinite, they will give a result greater than 0.5, so they will be closer to horizontal. Now let's work with our neuron and especially the result that we got. So we got a result of 1.5, so from 0 to 2, so 1.5 is somewhere here. Then on this 1.5 we apply the activation function, the sigmoid. So 1.5 on the sigmoid, it gives us a result of 0.8. Now let's draw a slope for this 4.8. So I'm going to take this okay. So this is the slope of our result at 0.8. What if we had a different result? Let's say that the result will be maybe 0.9 or something. So 0.9, maybe here is somewhere 0.94 or something like that. And let's also draw the slope for this result. We can see that here different results on the sigmoid are going to give us different slopes. And why is this so important? This is really important because we can see that, for example, this slope is steep, while this one going to be closer either to 1 or closer to 0 is much more shallow. And this is really important because we know that when we are far from some result, we need to make bigger changes than if we are closer to the result. And this is so important because it is telling us how much we can adjust the weights each time. If we are really far from a correct prediction, we are going to make a really big adjustment. If we are really close, then we will make some really small adjustment. The closer we are to a good result, the smaller it has to be the adjustments of the weight. And now, to make more sense, we're going to see this with the code using the numbers, so it will be more clear why this works. Here I have a new file where I have the sigmoid that we have already seen, and then the sigmoid derivative. The sigmoid derivative is the function that we use to get the slope of the sigmoid. Now let's try them with our values. So we have our result, which is equals to 0.8, but also our error right now is equals to 0.8. So how do we know how much we have to adjust the weights? To do this, we are going to multiply the error with the slope of our result. And we can call this adjustment. And let's print now our adjustment. And then adjustment. And I'm going now to run this one. So using these values, 0.8 as a result, 0.8 as error, we know that this is going to be our adjustment. What if we had smaller error? If we had like some really small error, so we were really close to a correct prediction, let's say just 0.1, if I run this, we see that the adjustment that we make is going to be really small. Now that we know this, let's go back to our whiteboard and let's do all the calculations manually. Let's add the adjustment. Equals to 0.17. Now, do we have to make the adjustment of 0.17 per each weight or just for some of them? Well, we will know this by multiplying 0.17 with the input. So this adjustment must first be multiplied with the input. So we're going to do that. We're going to multiply 0.17 with each pixel value of the input. So here we're going to have all the input values. So 0, 1, 0, 0, 1, 0, 0, 1, 0. So I just replicated what we have here. Now with this, we're going to multiply each of these with 0.17. Multiply with 0.17, and this one, let's make for them all 10.17. And this 1.17, and this is going to be equals to 0, 0.17, 0, 0, 0.17, 0, 0, 0.17, and 0. Now, this is telling us which weights we have to adjust. So where it's 0, of course, nothing is going to change. Where it's 0.17 are the weights that we're going to change. So now what we do, we take all the weights and we're going to subtract 0.17 on the weights where we have 0.17. So we subtract each single value from each single weight. So this will be, the next step will be all the weights. So these are all the weights. Let's replicate them right here. 0.5, 0.5, 0.5, and this one 0.5, 5, and last 1.5. The weights, from the weights we have to subtract this value. So on the first one we are going to subtract 0, so 0.5 minus 0. 0.5 minus 17 minus 0 minus 0 minus 0.17 minus 0 minus 0 minus 0.17 and minus 0. And so we're going to get our weights. The first one is still the same. The second one is 0.5 minus 0.17, so 0.33, 0.5, 0.5, 0.33, 0.5, 0.5, 0.33, and last one, 0.5. These are our new weights after just the first round of training. So this one are now our weights. And this one, we know it's the adjustment for each of them. Adjustment. What do we do now with these new weights? Now that we have finished the first round of training, it's the time to test the new weights to see what results we're going to get. So instead now of writing everything from scratch, we can say here we completed the first round. Now I'm going to remove all the previous weights and I'm going to try calculating the value with the new weights. So we take these weights. So let's remove everything that we have here. So this must be removed. Also, the final result of the weights has to be removed. And okay, this. And also the result of the sigmoid. This is going to change. And also this one. And so let's now use our new weights. So the first one is 0.5 still. So 0.5, no change, 0.5. The second one is 0.33. The third one, 0.5, 0.5. 0.33, 0.5, 0.5, 0.33, and 0.5. So the first one is equals to 0, the second one to 0.33, third one 0, 0, 0.33, 0, 0, 0.33 and 0. We're going to sum all of them. 0, 33, 33, 33, 66, 66, 66, 99 and 99. So the final result here is 0.99. What is the sigmoid of 0.99? So here we're going to put sigmoid of 0.99, and let's see what's the result. Let's now calculate the sigmoid of 0.99. Print sigmoid of 0.99, and I'm going to run this, and now our result is 0.72908, so we can approximate this to 0.73. And now we come back to our whiteboard, and here the result of the sigmoid, we said 0.73, and everything starts again like before. We know 0.73 is supposed to be vertical, so now we have to calculate the error. Here, to calculate the error, we are going to subtract 0.73 with the vertical. So also our error now is 0.73. And now we will need to do the same process we did before for the training. So we can see that now we got some improvement. Our error before was 0.81, now 0.73. Now we're going to do all these operations on our code with Python. Now we go back to our code, and here to the sigmoid I've also added the sigmoid derivative so that we can calculate the slope of the sigmoid. On our neuron we have now the input, so we preprocess the image. We have the weights, which they all start from 0.5. We have the activation function, which is going to tell us if the output we get either vertical if less than 0.5 or horizontal if greater than 0.5. From our output and the result, we can calculate the error. And now, for the training of the neuron, we're going to calculate the adjustment for our weights. So 0.6 is going to be adjustment, and the adjustment is equals to the error multiplied with the sigmoid derivative of the result. And so if we print now the adjustment, now we get 0.81, which is the result of the sigmoid activation function. It is telling us it is horizontal, so it's wrong. It's wrong, and this is our big error. And now we know that we have adjusted the weights of 0.1737 and so on, this long number. Now we know the adjustment, and we have to multiply the adjustment with the input and then subtract the value from the weights. So the weights are going to be minus or equals np dot, this is to multiply the input, so the input is the flattened image, with the adjustment. And here I get an error weight, so probably we have a typo here. Weights is this way, and so we correct also this one. And so after this we can print again our weights, and then weights, and let's run this one. So now we have our new weights, which are 0.5, 0.32, 0.5, 0.5, 32, 0.5, and so on. Now we have the weights updated. What would be the next step? To just repeat everything. There will be now no point to make any further code to see if the neuron is working correctly. Instead, much clever, we are going to put in a loop everything that we are going to repeat. So the input is always the same, so image flooding is always the same. These are the weights at the beginning that we choose randomly, so we leave them there. But from here, just after the weight, we're going to say for I in range of 2. And we put all the code below inside this loop. So once we arrive here at weights, it is starting again from the beginning. And now we're going to do this just 2 times. So let's run this and let's see what we get. So this is the first round, and we get this error, and then here is the second round, and as you see, the weights are still changing. Now, to see everything better and more clearly, let's print all the statements in order. So the first result, we can remove this. We can just keep vertical and horizontal. Then we can see the error. We can see each time the adjustment, and we can see the weights. Also, let's print a empty line so that we can discard each loop, and also we can say on which round we are. And we can say that by here print at the beginning, we can print at the beginning the round, print round, and round is equals to I plus 1. Because it starts from 0, so we start from the I starts from 0, so we want to start the count from 1, and we will see the rounds, and we can run this again. So we see round 1, our detection is telling us it's horizontal. This is our error. This is how much we are doing the adjustment, and these are the weights after the first round. Round 2, still it is telling us it is horizontal. This is the error. This is the adjustment, so smaller error and smaller adjustment, and then the weights. Now, let's try this 10 times. We need to use this as long as it's necessary to train this properly. So the less is the error, the better it is. Let's see that step by step. So round 3, it is horizontal still, but the error is slowly decreasing, and that's what we want. Round 4 and round 5. So round 5 is the most important, because that's where for the first time our detection is correct, and for the first time we can say that the image now is vertical and it was detected correctly. Error is 0.42, and let's see, if we go to round 10, we see that now the error is really small, 0.19. So the more we do this training, so the more rounds we make, the better our neuron is going to work. So we can do 100 rounds right now, and after 100 rounds we see that the error is 0.01, and it is saying vertical, and these are our final weights. Now, we have learned in this lesson how to train the neuron, what is the training of a neuron in general, but we did this with only one image. So in the next lesson we're going to see how we can do the training, adding also more images, not only vertical but also adding the horizontal image. This is all for the moment. See you in the next lesson.